My name is David. I'm data scientist from PicsArt. I'm going to be talking about recommender systems today, their development from classic era to deep learning. Sorry, my Armenian is not fluent enough to speak Armenian, so I will speak in English. So this is the outline of the talk. I will give you a brief introduction. Then we will talk in details about collaborative filtering. We will go through probably the oldest models, neighborhood-based. Then we will continue with matrix factorization models. And then we'll finish with one of the ideas how to use deep learning to solve the problem of recommending items. OK. So why is this important topic? Recently, the web makes a shift towards being more discovery-driven and less search-driven. You have an information explosion. So imagine you go to Netflix. You have millions of movies, not millions, but tens of thousands of movies. So you really don't even know what you want to watch. Or in Amazon, there are so many items that it's hard to decide which one to buy. So you really need some algorithm that will help you filter, personalize, and recommend items. So this is some numbers that show the value of recommender systems. So for example, 2/3 of Netflix movies that are being watched are coming from recommendations. Or about 1/3 of sales on Amazon are also being recommended. This is the way recommendations are used currently at PicsArt. You can see three screenshots of the items being recommended. On the first one, there's a clear topic. So something about nature, something about architecture. The second one is about nature and animals. The third one is some kind of like surrealistic edits. The idea here that we firstly want to personalize. Secondly, we want to make sure we don't overkill. So we don't show the same very similar items. So in terms of this topic, we have some animals, different animals, nature, flowers, trees. So kind of some amount of diversity is desirable too. So let's move to the second part. There are different ways how you can make recommendations. And collaborative filtering is just one of the ways to do it. It is by far the most popular, the most widely used. So that is why we will talk about this approach in details. And we will start with the neighborhood-based approaches. So the idea of collaborative filtering is that firstly, what data do we use? We use user-item interactions. So if John has watched movie Star Trek and then Star Wars, and then Rachel had watched Star Wars and Star Trek, and then she also watched Alien, we know they are similar, but there's one additional movie Rachel had watched that probably John is going to like as well, since they're similar. So this idea is the underlying idea of all approaches that collaborative filtering has. The main challenge here is that usually the user-item interaction matrix, or like a table where you have for every user, every item the user has interacted. Let's stick for this presentation with the movie example. It's just easier to explain. There are like maybe 30, maybe 40,000 of movies, and every single one of you have watched a tiny portion of them. So if we make this matrix or table, it's going to be sparse. The majority of entries are going to be empty. So this constitutes a problem. OK, so the neighborhood-based approaches are the earliest. And they used to be popular maybe, I don't know, maybe 15, 20 years ago. They are based on the idea of calculating similarity between users or between items. So again, as in the example I mentioned before, we tried to find similar user to John, which in my example was Rachel, and tried to use the additional items she had interacted with to recommend to John. the same idea with item-based, but now we compare items. So this just visually shows what I just said. This is John. These are all users. And out of all users, we find these most similar guys and use their interactions to recommend to John. How we can do that just in more mathematical terms. So we calculate, for example, Pearson correlation between user U and V, John and Rachel. And Pearson correlation is just covariance between user John and user Rachel normalized by standard deviations of the ratings on user John and user Rachel. By the way, I didn't ask, how many people work with machine learning? How many data scientists are here? So I just want to understand, should I go into, so how many people know Pearson correlation? Okay. Okay, so there would be some notation in this presentation. I will give intuition, but I will not go into details because we will not cover. It's not possible. So this just shows how to what extent they are on the same line. The ratings for John and ratings for Rachel. Then what we can do later, we can calculate for every single user similarity to John, and then select top K of them who had interacted with the movie Alien, that movie that we want to get prediction for the John. When we have these users, we calculate the weighted average of the ratings of those users, weighted by similarity, and this is going to be just our prediction for the John. So for example, if 5 most similar to John users have enjoyed movie Alien, most likely John is going to enjoy this movie as well. Okay, there are different ways you can measure similarity. The alternative measure is a cosine similarity, which measures the angle between the vectors that represent user or item ratings, but no, we will not spend time here. So what is the problem that we usually happen to see in the collaborative filtering data? Long tail distribution of the interaction of the items. So imagine again that we are talking about movies here, and movie Terminator, Matrix, Titanic, they're going to be very popular movies that will have a lot of interactions here. But the majority of movies are the way less popular, right? That is why they will be here having very small number of interactions. That might constitute a problem because our algorithm might start look, when it calculates similarity, mainly on these ones. And because of that ones, it will recommend as the most similar users who are enjoying popular stuff. And then as a consequence, it might recommend only popular users. This will, popular items. This will result in popularity or selection bias. So majority of our items that we'll recommend will be less personalized, biased by popularity, and the diversity of our list is going to be small. One of the workarounds is that we can just introduce a new term that will give a bonus to less popular items. So if M is the number of users and MJ is the number of users who rated this item, this term is going to be big for non-popular and items or movies. And this term is going to be small for popular items or movies. And then we can use this term in our similarity calculation to make sure it gives a higher weight to less popular items when it calculates covariance. This will kind of diversify the items we recommend. Let's go through a toy example. What is going on here? So this is the matrix of items and users that I was talking about. So those are users, those are items. We have a target user, John. And the first step, we want to see what ratings he had already provided. So he provided 2 ratings to these movies. And in the second step, we want to calculate the similarity of John with all other users based on the ratings he and other users had provided, and find top and most similar users. and use their rating information to impute missing entries in the way I had already described. So again, here it just says the same. So we predict the ratings for the target user, unrated items. And then after we made this prediction, we can just select top n by the score the item had received. OK, so the same idea, but just flipped around, is item-based collaborative filtering, where we, for example, for movie Superman, out of all movies, we try to find top n most similar ones. In this case, these movies happen to be Spider-Man, Batman, Avengers, based on the interactions. So if we go back here, for this movie, if we try to find most similars, we look at, we calculate similarity with these ratings for different items. And then the idea is going to be the same. We're just going to leverage this similarity information. For example, for user John again, we try to calculate predicted rating for movie Alien. We know he enjoyed movie Star Trek and Star Wars. We know those movies are similar. We can calculate the weighted average of the ratings with weights that are going to be similarity and get the prediction for the item Alien. Так, what are advantages of this method? These methods are really simple to implement. They could be very explainable. So as I said, you can explain to the user why you recommended the movie Alien because he had already watched similar movies. Disadvantages, it ignores similarity between in the item-based approaches, it ignores similarity between users. In the user-based approaches, it ignores similarity between items. And usually doesn't work very well with the sparse matrix. So let's move on to the next step of development of these algorithms, which are latent factor models or matrix factorization models. So the question we have left off was, can we actually use both correlations and similarities between users and items and in one unified framework? And the answer is yes. And latent factor models or like matrix factorization models can leverage similarity of users and items and provide recommendations just in one shot. So firstly, what is factorization? So if we are talking about matrices, this means that we can represent or express or reconstruct this matrix, the R matrix, which is a matrix of ratings, the one that I was talking before, a matrix of users and items. You can represent this as a multiplication of two other matrices. And why is this important for us? Because there is some result in linear algebra that basically if you have a matrix with the size m by n, and the matrix is fully specified, so you have values in every entry, and the rank of the matrix is k, then you can factorize this matrix by two matrices m, k, k, n without loss of information. So you can fully reconstruct matrix R by multiplication of matrices u and v in case one of the dimensions is equal to the rank of the matrix R. Why is this important for us? Because this actually is similar to what we are trying to do with recommendations, but with some differences. In case of recommendation data or collaborative filtering data, this matrix R is not fully specified. So the vast majority of entries are empty. We don't know this user and this item, would this user like this item or not? Majority of items have never been watched. This is one difference. Second difference, we have no clue what is the rank of our matrix because, again, it's sparse. But why we still want to use it? There is one underlying property of collaborative filtering data. As I told you in previous approach, neighborhood-based approaches work only because there is a similarity between users and there is a similarity between items, which means that these matrices are prone to dimensionality reduction. Basically, some rows and some columns of these matrices could be expressed by the other rows and columns. There is some correlation. This means, with some assumptions, this implies that the rank of these matrices should not be too big. So if we try to find matrix U and matrix V, and we get some small rank K, like 8, 16, 32, 64, there is a probability it's going to be enough to reconstruct with good enough quality the rating matrix R by using the fact that there are a lot of underlying correlations. And the second question is that, okay, but here the matrix was fully specified. Yes, in the case of recommendation systems, we will have like maybe less than 1% of items of entries here. But we still can learn these two matrices in order to approximate these entries that we have. And have a hope that it will reconstruct all missing entries with high precision. This is the underlying intuition, and this is how it could be represented. This is a toy example that will show you the presence of correlations of users and items in our data. So we have again here users, here movies, and you can see those movies, Nero, Julius Caesar, Cleopatra, are historical movies. And Sleepless in Seattle, Pretty Woman, and Casablanca are romantic movies. And basically, we already can see that those three are similar to each other, those three are similar to each other. Those users clearly enjoy historical movies because they have high ratings for historical and small for romantic. And those users clearly enjoy romantic movies since there are high ratings for those movies and small ratings for the historical movies. So again, we can see that users also kind of split into two groups. This might mean that our matrices are of rank 2. That will mean that if we want to factorize this matrix, we need to matrix U and matrix V, both of them with dimension K, which equals 2. So 7 users by 2, 6 items by 2. And what do these numbers actually mean? They represent numerically the affinity or the preference of the user towards different type of content. So we can understand that the first and second latent factors actually describe to what extent user 1 is interested in historical movie, to what extent user 1 is interested in romantic movie. And we can see clearly the first 3 users who showed high degree of interest in historical movies have a high value for the first latent factor. And by the way, we call it latent factors. And the small values for the romantic movies. And the same is true for guys from romantic groups. They have a high value for latent factor that is responsible for representing romantic movies, and small value for the historical. The same is correct for items. Again, those are numeric representations of items. And again, we have latent factor that, again, this is a toy example. This is not exactly the way it works. But, and the numbers are integral numbers. Really it's going to be real numbers, but it's just toy example. So the movie Nero, for example, has a high value for history, but small value for romance. But movie Cleopatra, interestingly enough, has a high value for romantic and history movies. So by just combining those two matrices and by multiplying them on each other, we can get the prediction for every user and item in our matrix here. At this point, the matrix is fully specified for the sake of example, so we have all values, but in reality, we will have a lot of missing entries. So for example, if we want to predict the rating for user 1, movie 1, we get the latent factor for user multiplied by the latent factor for the item, and we get 1. So how can we learn these two U and V matrices? So we start by randomly initializing numbers here, but how are we gonna approximate the correct entries? So again, everybody who had some familiarity with at least linear regression knows this. This is basically L2 loss with ground truth here and with predicted rating, which is just linear combination of our user and item entries of latent factors. So this is loss that we want to minimize. We calculate this over observed entries, over entries that have some ratings in our rating matrix R. We need to solve this to find the correct values for our matrix U and V by optimization approach, which would imply that we need partial derivatives of our loss with respect to components of user and item latent factors, which again, this is just a result of differentiation. This should be familiar to everybody who learned how, for example, linear regression, gradient descent works for linear regression, for the case of linear regression. This is algorithm, again, the most popular optimization algorithm in machine learning, gradient descent. We will go very quick through this. So what is happening here? We randomly initialize, as I said, matrices U and V. We make sure we're going to be taking into considerations only the observed entries. Then we will calculate the loss in this form for every entry, and in this form, not the squared form, because as you remember here, after differentiation, the power of 2 just cancels down. And then what we're going to do for every user component pair. So if we have M users and K components, for every for every component in MK, and for every item component, if we have N items and K components for this NK matrix, we will do this update. This is a gradient descent update that takes, in our case, at the first step, a randomly initialized value of user I, Q, latent factor value, adds, because the minus here goes here, learning rate by the value of gradient. And then we do for every, as I said, user item pair. And the only thing that we accumulate those values and do not make actually update, because update is going to be here simultaneously. This is how gradient descent works. The problem here that, as I said, M by K plus N by K could be a big number. So we could have M number of users like millions. The same is true for items. This might make it computationally heavy. That is why we can use stochastic gradient descent. Again, a very famous algorithm. The only difference here is going to be that we will randomly shuffle our observed entries, select one, and then we will calculate loss only on this entry, and then we will do update for all items of latent, for all elements of latent factor for user I and item J, and this is it. And after that, we will make an actual update. This will make it the way faster. So this algorithm is going to converge faster, but obviously gradient descent is going to go smoother. Okay, so this is not the only way to learn user and item matrices. There is since, as I said, there is just L2 loss. It has the analytic solution, a famous solution. Again, everybody who encountered linear regression knows it. So X transpose X, inverse X transpose Y. So we can use it, but in a very interesting fashion. So again, we randomly initialize these values, right? This is the first step. What we can do later, we can consider this kind of our data, and we can consider this. We can consider these to be our label. And we can try to learn the weights here. Not learn, just calculate, since we have analytic solution. The next step, we're gonna, again, consider this our data, these weights that we need to learn, and this our label. And do it for all items. And we will learn some weights here. The second step, we flip. We jump here. We say, OK, this is our data now. We just solve linear regression. This is our data. This is our label. These are our weights. We need to calculate them. We have a formula, plug in, calculate. Again, this is our data. This is our label now. We learn these weights. We do it for all users. And then we jump back and forth for the fixed number of iterations. And we'll learn some values here. So how do they compare? Usually, from the experiments I have seen, there are some papers that benchmark those approaches. Stochastic gradient descent usually converges faster, usually provides higher accuracy. But in the case of high sparsity, ALS could have some performance boost. OK, so how is on time? OK, I talked about matrix factorization methods. They used to be very, very popular for some time, maybe about 10 years. And recently, maybe about last 4 years, deep learning started to become competitive in this field too. OK, why people started to looking at deep learning and applying it to this problem? Because it showed some huge successes in different areas. For example, on ImageNet data, for the classification, you see during 3-4 years, there was a huge improvement that was achieved by just applying deep learning algorithms. And people started to think that maybe the improvement in results that they achieve in domains of computer vision, in domains of natural language processing, could be applied to recommender systems as well. And they started to think what they can improve. So the first question we need to answer: what could be one of the limitations of matrix factorization? So one of the hypotheses was that the simple choice of inner product that just linearly models interaction between user and item could limit the expressiveness of matrix factorization methods. This is two example. By the way, I'm going to be talking just about one famous implementation, one famous paper called neural collaborative filtering that is widely cited at the moment. But there are like tons of papers within the topic of deep learning within recommender systems. OK, what is going on here? So this is, again, toy example. In order to understand this example, we need to make some assumptions. We should use Jacquard similarity as a ground truth for similarity between users. Why we can make this assumption? OK, so Jacquard similarity calculates the similarity between sets. So it's an interaction over union. While we can consider users and items just sets of ratings. So how we can calculate it on this toy example? So imagine that this is a user with ratings to different items. This is user 2. We can first look at the interaction, which in this case obviously is going to be this. So those items that these both users mutually interacted with. And the union is going to be all items they have interacted with, unique items. It's going to be 4. So interaction is going to be 2. Union is going to be 4. So the similarity between user 1 and 2 is going to be 0.5. OK. So we can calculate this similarity to all 3 let's forget about user 4 for a moment. We can calculate it for all 3 users. And the second thing we should consider is that latent factors of the users and items in matrix factorization are placed in the same space. So inner product that can represent the similarity between users as well, not just user and item. And it is actually equivalent to cosine similarity, because if we consider vectors of user as a unit vectors, which is basically geometrically shows the angle between 2 vectors. So basically, if 2 vectors are similar, the angle between them should be small. So if we calculate this similarity between users, we can see that user 3 and 2 are the most similar. And that is why the angle is small. And user 1 is more similar to user 2 than to user 3. That is why his vector, we could place it somewhere here, because it is more similar to 2 and less similar to 3. The angle is bigger. So the idea is that we should be able to reconstruct the Jacquard similarity in the correct fashion by linear way, by just these vectors and angles. But let us introduce the first user. And when we introduce this user and calculate the similarity with all other users, we can see that user 4 is the most similar to user 1. That is why we either have to place him here or here. There are 2 ways, right, to make sure it's close to user 1. But both these placements are going to violate the second similarity, which tells us that user 4 should be second most similar to user 3. And in these both cases, it's less similar to 3 than to 2. So this is just hypothesis, and this is just a toy example that kind of supports hypothesis that maybe we are not able to linearly represent all the complex interaction structure between users and items. How to address this problem? One way is just increase the dimensionality of the vector. So not make latent factors of dimensionality 2 as was in previous example, but make it 3, 4, and more. The problem here is that we can cause overfitting, and making 2 big latent factors also causes computational problems. It's computationally heavy. The solution could be learning more complex interaction function with non-linearities. This is where we can use deep learning. But the first step could be try to generalize matrix factorization as just a network. How we can do that? So as the input we give 1 hot encoded items and users. So 1 hot encoding is that for every user, if we have m users, we give we sort them, and then if this user is out of m at the position k, at the position we will represent this user as a vector of zeros with the 1 at the position k. The same is true for items. Then this will go to embedding layer, which is just a fully connected layer. This is very similar to the way Word2Vec makes its training. This user and item latent vector is going to be analogous to latent factors from our matrix factorization for user and item. What we do later, we do element-wise product of those 2 vectors in layer 1. What does it mean? So if we have 8-dimensional user vector, 8-dimensional item vector, we multiply the first element of the user vector by the first element of item vector. Then we multiply the second element of user vector by the second element of item vector, and do just that, and we get again 8-dimensional vector here. That goes to 1 fully connected layer with sigmoid, for example, activation function at the end, since we're trying to solve, for example, binary classification problem. Why this architecture already generalizes matrix factorization? Because PU and QI are, as I said, analogous to latent factor vectors from the matrix factorization. We do element-wise product, so this is the kind of first step of inner product, and then we put some weights here, and then activation function. So imagine we get rid of activation function. Imagine we enforce these weights to be uniformly just one. We get matrix factorization in its most basic form. So we can already generalize matrix factorization as the network. But these weights don't have to be just one, right? We will learn some weights. And as a result, we will understand that some latent factors have higher weights, some latent factors have lower weights. So we already can make some improvement on top of that. But this is still linear because we have just activation function on decision layer at the end. How can we enforce more nonlinearity? Again, we can start the same way. We can start with the one-hot encoded vectors of items and users that will go to fully connected layer, embedding layer. And then we will just get a tower structure, like pyramid structure of fully connected layers with some activation functions, ReLU, for example. And in that case, we can concatenate. As a result, we will learn non-linear, more complicated interaction between users and items. What we can do with that, again, what the authors of the papers did with that, they fused both models into one. Basically, this is the first one I was talking about just 1 minute ago, and this is the second one I was talking about. They both do not have shared embeddings, so if we have user one-hot encoded vector, it learns separate embedding for the left part, which is a kind of generalization of matrix factorization here, and does element-wise product. But at the same time, there's one additional embedding that is learned separately for the MLP part, which is multi-layer perceptron part. And the same is true for items. At the end, we get representation that is achieved by the GMF, and then representation that is achieved by MLP, concatenate, and put it into the decision layer, where in the case of binary classification, we can use sigmoid, and then we train it with log laws. There's one important property to the way these algorithms are getting trained. As you remember, I told you that the observed entries of our matrix constitute a tiny fraction. We have tons of unobserved ones. If we consider all unobserved ones as negative, we will get a huge data. The training is going to be very slow, and even validation. That is why we can introduce the concept of negative sampling, which means that for every positive interaction, for every observed entry of user and item, we will sample negative items during training. And the number of items we will sample is a hyperparameter. This could work for two types of feedback, explicit and implicit. I did not mention it during presentation, but basically you can think about explicit feedback as the case when you have the ability to provide a rating to the item. For example, if you can rate movie on the 5-star scale, it's very good with 5, it's very bad with 1. That would be explicit feedback that could be modeled with just L2 laws. If we have only interactions that are kind of positive interactions, imagine like you have like in PicsArt, but you don't have dislike. Or you have buy, purchase activity in Amazon, but you can't express, I don't know actually, maybe you can express, but probably you can't express the negative attitude towards some item. But in this case, you can use log laws, but only in cases obviously where you converge the problem to binary. So if you will have, for example, number of clicks, you still need to get back to this one. So those are results. They have shown the top red line with red squares is the performance of the neural network algorithm, the one that I showed the last, the one that was fused, in comparison with some other benchmarks. And the most interesting benchmark is EALS, which is considered to be one of the state-of-the-art matrix factorization algorithms. You can see that comparison is made on different sizes of vectors. So as you remember, I was talking about embedding vector or latent vectors. So you see that with 8, 16, 32, 64, usually there is some improvement in performance for all algorithms, but neural network-based algorithm consistently improves consistently on the top. What do we compare? No, firstly, we compare on two famous datasets, benchmark datasets, Pinterest and MovieLens, that are widely used by community for benchmarking different algorithms. What is the metric we compare on? The metric is hits ratio. So hits ratio is quite basic metric. So imagine your algorithm predicts score for example, you have one positive item for the user, and you have sampled 99 negative. You have 100 items. Your algorithm make a forward pass on all these 100 items, gives a score to every item. Then you sort all the items by the score, and look at top 10, hits ratio at 10. If in top 10 items with the highest score that was given by your algorithm, the correct positive item, the one that we know that user has enjoyed, is present, we consider this as 1. If it's not present, we consider this as 0. And then we just calculate the fraction of the cases when we get the 1 out of all cases. And you can see here that, the NCF framework usually, no, not usually, in these particular cases, outperforms other algorithms. The second question that we might ask, is going deeper helpful? So these are values of the hits ratio, or it's hits ratio for a different number of hidden layers, starting from 0 to 4. We can see that if we fix size of latent vector, for example at 8, we consistently get an increase in our target metric, but the incremental increase is getting slower almost from the first or second layer, so it doesn't make sense for this particular task to go deeper than 4, but it still makes sense to add several layers. And the same is true for Pinterest. Okay, so I need to wrap up. So mainly what I was trying to show, the main steps the collaborative filtering had gone through the last maybe 20-25 years. I was talking about collaborative filtering just because this is most common way of providing recommendations, but it is not the best in all the cases. The field is quite interesting and evolving, because the majority of results that research community achieves in natural language processing or computer vision domains usually finds its application in recommender systems as well. And overall, it's quite interesting just because it is indeed possesses a huge potential to improve our daily communication, interaction with the content in the web and the applications. Okay, thank you.
Okay, I think I'm wrong. hyperparametrեր երկու ալգորիթմի դեպքում է։
Հա։ K-ը как раз latent factor-ի մեծությունն է։ Ну, это векторы. То есть դու ունես R matrix, որը MN-ա, ուզում ես իրան reconstruct անես M k-ով, N k-ով։ Այդ կան ինչքան դու կվերցնես, դա քո հիպերպարամետրը։
Let's suppose we have a product that we have a model where we suggest our conventions. And we collect data from users in variables. But is there any best practice when we should recalculate our model at some kind of data length or something like that?
Again, can you please repeat your question? I didn't.
Let's suppose we have a model which helps us to recommend something, and we collect a lot of data. So when there are a lot of data, we can recalculate the model, yes, retrain it.
Oh, of course you can.
Is there any best practice how often you should do it?
This is there is okay. The question was: is there a best practice how often to retrain models? This depends first on the model. If we're talking about collaborative filtering, there is no one rule of thumb that tells you this should be retrained with, like, I don't know, 2 hours, within 2 hours periods. The thing is that you should just consider is that as fast, the faster you retrain usually, the faster you react to the changing behavior and taste of your users. So it depends on the nature of data, on the nature of interaction of your user with your content. And depends. It also has a technical limitations because this will imply that you should use more computational power. So it's always just kind of the trade-off between again wasting computational power and being more reactive to the changing behavior of your user. The answer to this is just digging deep into your data. First, understanding your limitations. Secondly, understanding your data. And figure out some number for you. This is there is no one correct answer for all cases.
What are the libraries you are using to do your daily work?
What is
libraries? What libraries are you using for your daily work?
No, the question was what libraries do you use for the work? So if we are talking about just using kind of like vanilla matrix factorization. In our case, we use Spark MLlib if we are talking about matrix factorization. But if we are talking about deep learning approaches, our team uses different, but usually it's either TensorFlow or PyTorch. I mean, there are some other ones. So, for example, Python has a surprise library. Then Python has a implicit library. But Spark is just more robust. It,
so you are using TensorFlow or
PyTorch.
TensorFlow is more low-level, right?
Right.
It's more high-level. So which one do you prefer?
I prefer PyTorch. This is the answer to the question.
Still Keras can have PyTorch backend, right? And you still prefer Keras?
No, at least in experimentation, this is the library that I use.
In matrix factorization, we use such text similarity.
In matrix factorization, we use what?
Some text similarity.
Text similarity. Text similarity. So, okay, so what would be your matrix in that case? So, if we have user item matrix, in the case of text, you want to. The question was, can we use matrix factorization for text similarity? What would be your matrix in that case? Word vectors, you can directly already use vector of words. For example, if you have a bag of words, you have calculate similarity on bag of words. You apply TF-IDF and calculate similarity on them. If you have a word-to-vec vectors, it's even easier. You directly apply cosine similarity. If you are talking about comparing not just single words but phrases and sentences, you can either train models that do that, for example, doc2vec, or you can use the single separate words vectors of this sentence, sum them up, and then consider them as just representation of your sentence, and again calculate similarity. So there is no need probably for matrix factorization for this task. Все? Okay, thank you.